So we wanted to start this with a really good motivating example of why requirements-based testing and why all of this is really important, and scratch my head long and hard trying to come up with an example to grab everybody's attention, and by far the best thing we could come up with was the following picture that we discovered on LinkedIn. And I think this really highlights why it's necessary not to just test the overall performance of your system at the macroscopic level, but also to test that each component is functioning as it should. So we'll talk a little bit about functional testing itself. In DO-178C, you are required to do essentially two types of testing: the normal range testing. So this is checking that the values you get with expected inputs are exactly as they are specified. In other words, does the software do what it's supposed to do when you give it the data you're supposed to give it? But there's also a requirement for robustness testing, which is how making sure the system responds in a safe and predictable way when given inputs that are outside the expected range. And this is really important because we accept that no system is ever devoid of bugs. So testing that a certain component can deal with faulty data that it may be fed from other components, or this may be faulty data from hardware instruments, being able to accept that data and not undermine the effect of the system any more than it already would be, is a very important part of safety critical software. There are different levels at which you can perform your testing. Lots of people have heard of unit testing. It's kind of the most popular paradigm outside of the safety critical domain. In safety critical, you are going to encounter probably 3 levels of software. From low level testing, does each individual component in the system function as it's expected to? Usually by excluding the effects of other components, you are testing one piece in isolation. And just because every single piece of your software is executing correctly or functioning correctly, that doesn't mean that the system's going to work, because you may have wired the independent components up incorrectly. So integration testing is really checking that those interfaces between software modules is working as expected, and that the data is being passed in the correct way, and that everything works together at a higher level. You'll probably come across software integration testing and hardware integration testing. So that's checking that the software is interfacing with any of the hardware abstraction layer correctly as well. And finally, you get to system level testing, where you really are testing the whole software or very large parts of the software in ways that are similar to how it's going to work in the field. So you, instead of at a low-level test or a software integration test where you might be introducing data into some subsystem, during system testing, you are usually using the software's external interface and driving it as it would be in an aircraft or other vehicle. There is also a concept of black box and white box testing. Black box testing, basically you're saying that the software is a black box, it is opaque, we can't see inside it, and you're only providing inputs and observing the outputs, not making any judgment or any measurements of anything that's going on inside the unit under test. The other side of the coin, the opposite of black box testing, is called white box testing, because white's the opposite of black, but it really should be transparent box testing, really, because here you're looking inside the system and maybe you are asserting some of its internal behaviors. And this is sometimes used because software is not always purely functional. Sometimes there are side effects, and sometimes it's necessary to observe the side effects of code. However, the disadvantage of white box testing is a greater maintenance effort if you do replace the implementation, you rewrite the software into test, then the test may no longer work as expected. Black box testing, because you assume nothing about what's inside the box, you're only testing its external interface, those tests are still valid even if the implementation completely changes. So there is some guidance within DO-178C, and I should state at this point that I'm going to talk a lot about DO-178C because Rapita do lots of work essentially in the software domain, but a lot of what we're going to talk about also applies to DO-254 and hardware requirements, the ground systems, DO-278C and things like that as well. So we're going to reference DO-178C, but almost all the concepts are going to apply to other safety standards as well. So what does DO-178C say? Well, it has a lot of tables such as this. This is essentially giving the breakdown of what you have to do for different design assurance levels. So the design assurance level roughly corresponds to how critical a component is. In DO-178C, the highest level is level A, and you'll notice that we have to do both high level and low level requirements testing, both robustness and normal range test. For the highest levels, we have to do this with independence. So they have different teams of people responsible for each component. So there is no untoward sharing of information that could weaken the ability of the testing to detect errors. So here it is again in a slightly less tabular view. So you always have to do this normal and robustness testing regardless of your design assurance level. The testing for DAL-D is slightly relaxed compared to A, B, and C. And independence, as I mentioned, is necessary in order to avoid problems. Too much information about an implementation could lead to blind spots in the way some piece of software is tested. So the testing is the overall testing is accomplished by different levels. So there is some level of both integration testing, low level of system testing. It's not necessary to test every single value that can be given to a particular function. This would be almost infeasible in most cases. The guidance is to try and test equivalence classes of values that are expected to give similar functionality. Testing can be done black box or white box level. As I mentioned, black box has some advantages. You may need to provide extra validation of why you're doing a white box test, for example. And as with most things, DO-178C only tells you what is necessary, never how to do it. So there is certain flexibility in how you go about your test campaign, as we will talk about shortly. But now it's time for me to hand over to Cary from Jama Software, who's going to talk about requirements traceability. So over to you, Cary.
Thanks, Matt. Welcome, everybody. So Jama Software, if you haven't heard of us, we're really the #1 tool in requirements management. Essentially, our platform allows you to configuration manage requirements, test cases, risks, and keep them all traced together using live traceability. Some of the capabilities that we're going to see today are the configuration management of requirements and the reviews for those kind of independent checklist reviews. We work with all different kind of customers in aerospace and defense, from avionics systems to the aircraft manufacturers. One of the things that makes Jama easy to use right from the start is our built-in template for our airborne systems. So we provide support for ARP 4754, DO-178, DO-254, 4761, and 326. This helps you really start using the Jama platform immediately out of the box, and facilitates the ease of analysis and demonstration of compliance to these standards. As I said, one of the things that ties everything together is live traceability. And one of the things we're very known for is tracing not only our own internal data types, but allowing the traceability to lots of external tools, including Rapita Systems. Another thing that makes us unusual is our collaboration capabilities within the tool. So if you are managing requirements today in standalone Word documents or spreadsheets and having to demonstrate traceability between your system requirements, high-level requirements, low-level requirements, you have to manually create links across all of those sections of the document and figure out how to track that and then demonstrate who is making those traces and who authored those individual pieces. It's really impossible to do in documents and very, very, very risky to do. So we automate that kind of thing and enable collaboration across that kind of information, which we'll see. This context-based collaboration is built into the application, and I'm going to show you what the contextual collaboration looks like for when we review checklists. I think I'm just going to share my screen right now. And I find the right button. Here it is. Okay, so I have a Jama project open, and I talked about the traceability. This is an out-of-the-box framework that allows you to essentially, it comes with a predefined schema of the types of objects. So in DO-178, you have to trace from, it begins with system requirements. You have to trace from the system requirements to high-level requirements and low-level requirements. Jama has this built-in schema that allows you to consistently make accurate traces. And then when you're wanting to analyze those traces and prove compliance and completeness because of this sort of schema under the covers, it really allows you to easily spit out the kind of reports for compliance purposes. One thing that is really nice with Jama is that it's all web-based, so you don't have to teach people specialized menu clicks and button clicks. When you're looking at requirements, you have a nice easy view of spreadsheet type of view that you can edit from. You can turn it around. So if you have pictures and formatted text for requirements, the Jama system can handle that as well. We have the built-in configuration management. So if you were to change a requirement, we keep track of the versions of that requirement. So this particular requirement is on version 1. If I were to change the requirement, it keeps track of the versions for you. And it keeps an audit trail. So now I know who was the author of this requirement, who edited the requirement along the way, the author of this requirement, who edited the requirement along the way. And this is really important to be able to, especially when you're going into review, to keep track of the independence. With traceability, we have the schema here. So if I needed to examine the way that we're decomposing requirements between system level and then the software high level and low level requirements, I can see that here to be in the tree on the right, on the left. I can see this particular requirement and follow its decomposition down. I can also see a live trace view. And so these trace matrices aren't something that's put together after the fact. I can see this one particular requirement is traced and follow that traceability all the way down to multiple lower levels of the high level requirements and the low level requirements. Jama also helps you with the writing of requirements. So writing of requirements in for DO-178 compliances, something that's pretty challenging for software developers that are new to working in this world. And we help you do that by incorporating checklists. So some of the checklists are very complex for DO-178. You have to look at all of the high-level requirements. Are they complete? Are they leaving no undefined conditions? Are they written in such a way that they are using unverified, that they're not using unverifiable terms, right? You can't, that flexible, easy, sufficient. So a lot of people will put together these checklists that people will then use to perform independent reviews of these requirements. Our contextual collaboration enables you to really do that. So here's just an example of a checklist review for some requirements. I've got the requirement. I can see the checklist right in line for the reviewer that the reviewer's looking at. I can see some collaboration. So for this particular requirement, it's not really verifiable the way it's written. And so, teaching someone how to do this is pretty much just like the way you would redline Word documents. So this enables you to really kind of segregate those who wrote the requirements from those who are reviewing the requirements. I can see that for this example, I'm reviewing it myself, but you could see how many reviewers there were, the progress, the review activity, that sort of a thing. So when really DO-178 starts with the definition of the system requirements, and then our traceability rules and allow you to enforce the traces. It then requires you to decompose the system requirements into high-level requirements, and then further down into low-level requirements, and requirements into high-level requirements, and then further down into low-level requirements. And you really need to adhere and assess each of the requirements within the development lifecycle. And then only after all of the high-level requirements and the low-level requirements have been independently reviewed and approved can implementation of the source code begin, right? And from there, independently reviewed and approved by V&V software experts. I think Matt is going to take you through that.
So I'm going to talk a little bit about the DO-178C life cycle as a whole. There are lots of stages involved. So there are 4 main checkpoints that you need to be aware of. And these are called stage of involvement, or SOI or SOI, depending on how you say it. At the very beginning, SOI 1 is basically a check that you've got all of your plans in place. So you have to explain exactly what you're going to do, how you're going to do that, and you also have to list all of the software and tools that you're going to use in this plan. It's really important to spend as much time as you need on this section, because whilst plans do evolve and it is almost inevitable that some changes have to be made, it does take time to do this. It is better to get your plans in place and not have to resubmit anything if you can avoid it. So at the end of this, the plans are presented, and the SOI is essentially a gatepost to make sure that everything is in place before you move on to the actual development phase. This is where things actually get implemented, get fleshed out, etc. It's always a piece of advice that that we'll give customers and potential customers to try and think about doing as much as you can as early as possible. Think about your verification requirements and your testing at the very start. The more work you put in early on, the easier the end of the project is when things are getting tight and deadlines are looming. So essentially, the earlier you find things, the cheaper they are to resolve. You may not be able to do on-target testing straight away. There may be hardware development going on in parallel. There may be limited availability of things. So often on-host testing is a good way of getting started on the process and checking that everything you need is in place and working. You move on to performing the actual function testing in anger in the verification phase, and preliminary results are presented to the authorities at SOI 3. And then finally, your full run for score. So just to skip back, by SOI 3, you should be able to run your tests, have an good idea that they're all going to pass, and that your other verification artifacts such as your code coverage or your timing data is also available at that stage. Finally, comes the formal verification, the conformity review and the final submission of all of your actual evidence. So part of the core of DO-178C in terms of requirements-based testing is that you should develop your software from requirements, and you should develop your tests from requirements, and then you should run those tests against that software. And that's why traceability that Cary demonstrated in the Jama tool is so crucial. Everything has to come from a requirement to have value, because if you can't write a test for a piece of software unless you know what it is supposed to do. For all you know, the software is supposed to crash or segmentation fault or whatever else. Without having written down what the software is supposed to do, you cannot effectively test it. However, there is still some value to having tests that may not correspond to a requirement. You can use this for development purposes. You can, for example, write tests to just check that code coverage is achievable on a piece of code. It's possible to write a bit of code that you can't achieve full coverage of, and we'll talk about that a lot more in the code coverage seminar in 2 weeks' time. And there are other reasons why you might have tests that don't trace to requirements, or they might not trace directly to functional requirements. You ought to perform testing for timing analysis as well. So worst case execution time analysis, etc. You'll still have test cases, but those won't be functional requirements. Those tests will correspond to non-functional requirements. On host versus on target is another hot topic. The older standard, DO-178B, was much less specific about this. As things have gone on, and on target development tools, on target code coverage tools, as they've improved, the authorities are pushing more and more to doing your testing on target. And the ultimate reason there is that it's more representative of the system that you're actually putting into production. The mantra goes, you should test what you fly, and then you fly what you test, essentially. And what is actually going out into production is a fully tested system. You can still do parts of your testing on host. You will have to justify why you're getting the same value as you would on target. So you may have to perform some extra work to demonstrate that your on-host environment is just as capable of detecting errors as your on-target environment would be. One reason you might be doing on-host testing at all is, again, as I mentioned earlier on in the development process, the hardware may not be finalized, available, etc. So the ability to start testing on host is pretty crucial. And if you are able to reuse your test cases on with an on-target test as well, then that's a huge amount of value because you're not repeating the work of writing those test cases. And again, you're detecting errors earlier, they are cheaper to resolve. If you need to change your requirement, it is much better to identify that early because there's a knock-on effect in changing requirements. So we'll talk a little bit about how testing is actually done. Previously or early on, a lot of testing was manual. You drive the software from its external interfaces and observe its behavior. Manual testing is very labor intensive, and generally people are using automated testing more and more for the obvious benefits. Some types of software are more amenable or for manual testing. You may find that more in higher level software with user interfaces, cockpit display systems, flight management systems, things like that will still have an element of manual testing involved. So automated testing, as the name implies, there is a hardware software tooling in place that is running your tests, driving the software under test, providing the inputs, checking the outputs, etc. And as with any piece of software that replaces any of the processes in a DO-178C project, unless its output is reviewed, then tool qualification is necessary just to ensure that that testing tool is behaving and you can trust its results. So on the subject of tool qualification, there is a document, DO-330, describes exactly what needs to be done. One of the key things to bear in mind is that tool qualification is the responsibility of the applicant. It's not the responsibility of the tool vendor. The tool vendor, such as Rapita, we will try and provide as much help and assistance as possible in the process, but ultimately tool qualification is the responsibility of the vendor, which means that tools that don't come with qualification evidence, they can still be used, but the tool user will be responsible for reverse engineering the requirements of these tools, right, and demonstrating that they've been adequately tested and they function as required. But if you're buying an off-the-shelf tool which has a qualification kit, then this saves a huge amount of effort. It is much easier for the tool vendor to write down the requirements and write the test cases than it is for you to take a third-party tool and do that work yourselves. I'll talk a little bit about some things that you may want to consider when selecting a tool. For example, how easy is it to write and specify test cases? There are a spectrum of different testing tools, from frameworks such as Google Test, which just provide a software framework for you to write your tests directly in the language that your code is written in. They're often very quick to get started, but there is a steep learning curve, and essentially you're required to understand the programming language or software is written in order to be able to write tests. Now, software development and software testing are related but different specialities. It is preferable if your test engineers don't need to necessarily understand the language the software is developing. They can concentrate on reading requirements and translating those into test cases, as opposed to trying to figure out pointers and private and public variables, etc. So that's an important consideration. Does the tool support white box testing? If you need to, for whatever reason, inspect the internal state of your software, can you do that? Do you have different ways of specifying tests? Sometimes a programming language or scripting style approach is beneficial, whereas sometimes a more simple approach is beneficial. And we've mentioned the need for supporting, for example, private data and things like that, being able to get at these private variables without having to write boilerplate code, friend classes, things like that is a productivity benefit. And automatic generation of the test harness and test code is a benefit as well. So the test harness is everything that supports executing a test case. So an example of that would be a piece of code that initializes some data, and then it calls the unit under test, and then it checks the result. Being able to run tooling on the command line is a great benefit when it comes to try and automate this whole process. In an ideal world, you would be developing your test cases in line, in parallel with developing your software. And you can automate running these test cases on a continuous integration server. Other things you might want to consider are whether the tool will, how flexible is the tool? Can it fit into an existing software and test architectural environment that already exists? It's very rare for projects to start from scratch. You're usually inheriting some amount of infrastructure from a previous project. How easy is it to integrate the tools? Can you get any support? Another disadvantage of open source testing frameworks is there is maybe documentation available, but no actual technical support from people that can guide you through the process. Automation and merging are hugely important things. You want to eventually come up with a piece of evidence that you could submit to your certification authority. So you need to be able to collect data from multiple test cases and aggregate things like code coverage across those to demonstrate that you've tested your software adequately. Can you merge the testing domains? You might be able to do some testing on host and some testing of low-level functionality on target and then merge those together, for example. How easy is it to analyze the results? Again, being able to quickly turn around test cases to understand why they failed is very important. Can you look at the source code, see what code was executed, what happened inside the tools? Can you get a high-level overview of your test results as well as the detail? Also, traceability. This is a key thing. We've talked about this, and it's difficult to overemphasize it because it's so crucial to all of the DO-178C processes. So how does your testing tool integrate with your requirements management tools and other parts of the life cycle? And finally, can you embed your testing in a larger framework such as a CI tool? And finally, at the very end of the process, can you export the results in a format that's acceptable? If your results are provided in a proprietary format that requires a license to view, well, your authorities are almost certainly not going to have a license to do that. The submission format needs to be something that they can easily open and view. Other non-functional, non-testing related requirements are things like licensing. You need to consider how large is the tool, how large is the team of people that are going to be writing tests. Can they share licenses? Can you migrate licenses across international borders? I know there are international companies that have testing teams in different places. If you have licenses that are floating and not geographically linked, then you can get more for your money by having people testing your software at night, developers develop it by day in different time zones, etc. And finally, do you have the qualification kit available, all of that evidence that your testing tool works correctly and what those requirements are? So with all that in mind, I'm going to give you a brief demonstration of the Rapitest tool now. So here I am, Hall of Mirrors effect as I share my screen. So what does Rapitest do? Well, Rapitest allows you to take a description of your test cases, and it will build the test harness and generate code that can be compiled to run on host and on target. And the end result is a report of functional testing alongside any additional metrics that you might want to measure, such as code coverage or execution time. Here's an example Rapitest report from some test cases that were executed on host. I can see my overall pass-fail results based on test cases and individual assertions inside test cases. And I can explore this in a bit more detail. If I expand this out, I can see here are the individual test cases that I ran. Where we open these up, we can see assertions that that make up individual test cases. Every test has an implicit assertion that the software, the code under test actually finishes execution and doesn't crash or do something else as it's executing. And then you can specify in your test additional assertions, additional things that you want to validate. You can additionally have assertions based around exceptions. So if your code ought to throw an exception when passed certain input data, you can actually write a test which will catch that exception and pass if the expected exception is raised. Most importantly, when a test fails, you'll see what the actual result was versus what the expected result was, so you can understand why that test has failed. Also, the assertions themselves are flexible. When working with floating point, it is often necessary to have some sort of tolerance. Floating point implementations can vary. And importantly, the tolerance here can be absolute or relative. This is an important consideration, and maybe this will be written into the requirements as well. But if the expected result is 0, then the only value within 0.01% of 0 is actually 0 from a mathematical point of view. So beware that relative tolerances can become more and more strict the smaller or the closer the value becomes to 0, and that sometimes an absolute tolerance is preferable instead. As well as seeing the test results, we can also check results versus requirements. And here's where the interface with tools such as Jama Connect are really valuable. With Rapitest, we can import requirements from an external source using the RecIF requirements interchange format. Or alternatively, any other machine readable format is possible via a simple script. And pulling the requirements in allows us to, first of all, attach tests to requirements. But we can also report on requirements that don't have a test case. And we can also respect the hierarchy of requirements. So we can pull in both the high-level requirements and all of the levels in the tree as these are broken down into low-level requirements. And then finally, we have test cases for these low-level requirements. And we can see the actual test, the text of the requirements summarized here as well. In terms of how we actually write tests using Rapitest, there are a variety of different formats. Here's an example of a test written as a spreadsheet. This format exists through requests from customers. They wanted a format that was non-proprietary and easy to review. Another thing that's important to stress in the requirements-based test process is it's not simply enough to just have requirements and then have requirements-based tests. These requirements need to be correct, and the tests that they correspond to also need to be correct. And the way you get to that is through review. So not only do you have to think about how easy it is for tests to be written, you also have to think about how easy is it to review a test. Here, all we need to do to review this is simply to email a spreadsheet to somebody. They don't need a license for the Rapita tools to be able to open this, review it against requirement, etc. The test format allows you to easily specify the scope, what is your unit under test. You could list several units here if you want to do an integration level test. We can set up some local variables. In this case, this function takes a struct, and the structs are often passed by reference, so we set up some data first. We can stub out sub-function calls, and this is done for a variety of reasons. For example, we can fake or stub out hardware interfaces, sensors, for example. We can also perform fault injection and these abnormal range tests by stubbing a function and forcing it to return a certain value. Finally, we have the test description itself, which has some metadata at the top where you can see here we specify our requirements. And then we have a series of rows representing actions in the test. We're going to initialize our variable. We will configure the stub to behave as we expect, and in different test cases, it behaves differently. Finally, we call the unit under test, setting the inputs as appropriate. And here we can handle enumerated types and macros naturally, because we have a database about the source code and its type system. And finally, we list a series of checks or assertions to be performed at the end. You'll notice as well that we are not using the C syntax for specifying pointers. Again, the idea is that somebody can review this without necessarily understanding the C language or the Ada language. We also support Ada and C++. People can easily see that that is a pointer to this value. This is a pointer type, etc. So the rows of the test represent the steps, and these columns represent test vectors, and you can have as many test vectors as you want, and you can create additional test vectors easily by simply copying and pasting. One of the disadvantages of this format is we have limited ability to validate the data that's being entered. So for that reason, we also have a second format, which is similar in structure, but these tests are written directly in the RVS user interface. The advantage here is that if I, for example, create a new test local, because we have that database of information about the software, I create a new, if I type it correctly, we create a new test local. The tool knows that this is a record or struct type, and it's automatically pulled the fields out, and I can then fill these values in. You'll also notice we've got a warning now saying that we've created test local, but we've not used it anywhere. So we're highlighting to the user that there might be mistakes in there, etc. So this format is much more guided. It functions in the same way as we have rows corresponding to test actions and columns corresponding to test vectors. We can also open the source code in another tab, which is sometimes useful early on in the development stage. And we can do things, we can go further than your simple black box test. We can do things such as perform code injection, where I can inject extra code at a specific location. And this will allow us to actually inject code. Maybe there are, for example, here are some local variables. I maybe want to set or reset a local variable. Maybe there's a register read that I need to mask in some way. This can be done using the using the code injection system. Although Rapitest was designed to avoid you having to write source code, we of course give you the opportunity to do that, just in case there's something very specific that you need to do for a particular test case. All of the test results, once you're finished, once you've written your test, you can easily build that into an executable, and you can group your tests into test suites and select different test cases to run. There are also options to run only failed tests or run only newly added tests. And this will compile the test into source code and then into an executable, and then that executable can be run anywhere. There are no runtime dependencies on the Rapitest tool, so you can run it on host, you can copy it onto a different PC and run it, you can download it onto a target computer and run it there. There are no restrictions. We can export the data in a variety of different formats, the simplest of which is simply a plain text format that's guaranteed to be readable essentially anywhere, and provides us with our high-level summary of the individual checks as well as our requirements information. So we can close the loop and export test passes versus requirements as well. So you can export that back into your requirements management tool and complete the traceability loop. Finally, we also have plugins for continuous integration systems such as Jenkins and Bamboo, where you can see your test results right in the dashboard. You can view historic results, and you can also see your requirements coverage in the dashboard and dive in to get more details about a particular specific test case. Sorry, it's logged me out, but bear with me 1 second. How you can tell this is a live demo and this isn't all just pre-canned data. So yeah, you can click on any particular, if there was a particular nightly build that had a large number of failing tests, you can click and dive in and get more information about exactly what which tests passed and failed, etc.
Okay, first up from Pedro. I think this is a question for Matt. If we have safety requirements to state what is the expected behavior of the system when stimulated by out of range values. So I might need to reword that a little bit. So do we have safety requirements that state the expected behavior of the system when we are simulating out of range values? Is that correct, Matt? Does that make sense?
I found the mute button. Yes, I mean, your requirements have to be clear in specifying what the expected behavior is in order to be testable, and that has to be something that is quantitative and not qualitative. So this is something that Cary mentioned in her presentation, some of the checklists that you have to go through. Avoid things that aren't directly translatable into a yes/no answer. I hope that answers your question. If not, please let us know.
Absolutely. Okay, next up, I've got one for Cary here, which is, are the checklists you showed in your demo for Jama, are they customizable?
That's a great question. So yes, they are totally customizable. Many companies already have their own checklists authored. You can import them in via Word or Excel or author them natively into Jama. You can also purchase checklists from us that are authored by Affusion, which are already pre-imported as well. And then you can tailor them to your heart's delight.
Great. Thank you very much, Cary. Back to Matt for this one. It's a bit of a long one, so bear with me. When you say black box tests are written using from software design, is design mean the low-level requirements? For DO-178C test cases, should there be requirements based? These should be requirements based. 6.4.2, you need to have robustness requirements. Is software design an input to team developing the verification cases?
It's essentially a black box and white box can apply at any level of testing, but essentially your high-level requirements will trace to system tests, and then they'll be broken down into low-level requirements, and then your low-level requirements will trace to individual unit tests. And there are all sorts of checks that you need to do at every level in the process to make sure that you are following the design and everything is referenced and traced back as necessary to all the way back up to your original design document.
Excellent. Thank you very much, Matt. And another one here for Jama. So this is for you, Cary. Sorry, just checking that. Yeah, how does Jama support the reuse of items into different projects?
We have reuse capability built right into our software. And so while I showed one project that had lots of different items, you might have many different projects that are on different baselines of each other or different variants of the item or the component that you're building. And we allow you to reuse those requirements as well as keep them in sync. So if a requirement or a test or a piece of architecture changed in one project, I would be able to see which projects that was reused in, and I could accept the change or not if I needed to.
Excellent. Thank you very much. Okay, so let me find another here. Okay, yeah, so this is one for you, Matt, from Puria. How do we define non-functional requirements, in brackets, quality, interface, environment, etc.? That's part one of the question. Part two of the question is, where do we define system interfaces and architecture to define the requirements?
Yes, so I'm not sure exactly what's meant by the first page, but a non-functional requirement can still have testable attributes. So a good example of a non-functional requirement is timing based. So something must happen within 100 milliseconds. You're not saying what the functionality of the software is. You're testing some other aspect of that. Sorry, I'm just going to quickly reread the second part. So I think the second part was addressed to Cary, I believe.
Yeah, so in Jama, we have the capability to not only capture the requirements themselves, but also the architecture. So you can demonstrate the allocation between architecture and those requirements. And they're essentially defined as separate element types within the Jama project.
Fantastic, thank you very much. And Cary, while I've got you there, I've got another one for you. Okay, yeah, this is an interesting question. Does Jama review, or so the Jama review aspect of the tool, does it flag if the review independence is not adhered to?
Yeah, that's an interesting question. So the review itself won't show you, it won't like prevent you from creating the review. However, it will show you who the authors are, and it will show you who the reviewers are. And then through reports and filters, you can ascertain those exceptions. So where you have a deviation, you can see where there's a misalignment.
Okay, thanks for explaining. And we're coming up to the hour mark here, but I think we've got time for one more question, which is, this one's for Rapita. So the tests you executed in the demo, Matt, are they hardware? Is that a hardware in the loop setup you were using?
That particular one was just an on-host software unit test. We can do hardware in the loop testing with Rapitest. We can call arbitrary APIs and functions as part of a test, so we can talk to hardware test equipment if we need to.
Fantastic. Thank you very much for that, Matt. Okay, maybe I can just sneak one more in for Cary while we've got you here, which is, does Jama allow you to implement a formal requirement standard and verify it automatically?
So we do allow you to define the requirement standard as a process document, and then we, through our reporting structure, allow you to kind of ascertain whether the requirements engineers are following the processes within that. Deviations would be found through exception reporting